So, you know, we're data junkies around here, so contribute to our addiction by filling out the survey for Shamila's work. Okay, so you'll notice under today's announcements, there's not much left to say. The final exam starts tomorrow, which is quite a deal because it doesn't exist yet. So Wade and I, we're like, yeah, we'll be up late tonight. I'm also giving a talk tomorrow. That doesn't exist yet either. There are also, yeah. 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 Yeah, so you should be hoping that we just never get it done, right? You should all be hoping that we never get it done, but we will. Okay, so let's start working. We still have a lot to do. Believe it or not, we still have an algorithm to finish and one more to learn. Yeah, yep, you got that. I assert, though, that by the end of the discussion, and by the end of talking about that algorithm that you have yet to learn, you'll be like, oh yeah, I already knew all that, okay? So that one should feel good, but it's only going to feel good if we finish talking about Prim's algorithm. And we can't get through that until we do a little bit of a warm-up. So my warm-up is to ask you to characterize the difference between those two graphs. Talk to me, this is our last chance. We got to have our heart-to-heart now. Yeah? One is connected, the other one is not. I think I can figure out which is which. This one is, whoa, green, not connected. That means there exists a pair of vertices between which there is no path, and this one is connected. Okay, that's a good observation. Is there anything else you'd like to say about it? Yeah, Jeremy? Yeah, it's more than just connected. It's nearly complete, right? There are tons of vertices, or tons of edges here. When we look at them, if we just glance, if we give a human word to the description of the difference between them, we might say, this is dense. The number of edges here, or the edges here are kind of dense relative to the vertices. And here we look and we go, oh look, there aren't very many edges. That graph looks sparse. Those two keywords are actually technical keywords. This one is sparse, and this one is dense. There is no actual explicit technical definition of sparse and dense, but they are commonly expected to be the following. In a sparse graph, M is big O of N. That is, we're not saying where those approximately N edges are, but the number of edges is proportional to the number of vertices, okay? It doesn't mean it's a tree. It doesn't mean it's connected or disconnected. It just means there just really aren't very many edges, okay? Images induce sparse graphs, okay? Think about that a little bit. For example, like in MP4 and MP7, you were working on sparse graphs. Okay, on the other hand, in the case on the right, we can't necessarily do better than to say that M is big O of N squared. That is, it's likely to be a tight bound. Now, this is the part that's kind of under controversy. Do I get to put a line through there? Is it theta of N squared? And how do you characterize a graph that has N log N edges? That's where the ambiguity in the technical notation comes. Usually, this is the one that we hold to be true. We call a graph sparse if it has big O of N edges. or anything less, obviously. And the one that's not quite so universally accepted is to say that a dense graph has on the order of n squared edges. And what's in between is just a graph, okay? It's kind of how I think about it. All right, any questions about that? I'll let you decide what to do with these observations as we analyze Prim's algorithm. So last time we went through the execution of Prim's algorithm. It fell on a graph to solve a minimum spanning tree problem. Now, just to remind you, minimum spanning trees require a connected graph, and the edge weights can be anything. Connected undirected graph, and the edge weights can be anything. And we want a spanning tree of least total cost. Now, I'm going to go through a couple of iterations of the algorithm that we talked about last time. And the way you should be thinking about it is, how long does each of these steps take? So rather than viewing the algorithm, the steps of the algorithm as, how are we solving the problem, I want you to be thinking about it in terms of efficiency. In particular, I want you to observe and think about the cost of the priority queue and the cost of the two iterations here. So there are priority queue operations and there are these iterative operations. I want you to be thinking about those. Okay, so how does this algorithm go? Well, if you recall, we initialized all of the current best ways of attaching each vertex to the solution at infinity. It's the best we know right now. And we initialize some start vertex to have cost of 0 of attaching it to the optimal solution. And that's where we start. So that's the initialization. Now the algorithm goes like this. Oh, I should also note that when we set up this priority queue, it's of the DVs. So there are n elements in it. Forgot to say that part. Okay, so let's start this algorithm. Find and remove the minimum D unlabeled vertex. Which vertex is it? Please say it. This is our last chance. Which vertex has the least cost associated with it? A is right. Very good. Okay, so I'm going to make note of that. We're going to remove it from the structure. I'm going to label it by putting it sort of to the left of a fancy line. Okay? You would be putting it in a set if you were writing code for this, but I'm going to put it to the left of a fancy line. And then we do the update step. This right here is a for loop across incident edges, and there is this embedded if statement that checks every incident edge to make sure it's going across the label, across the horizon into the unknown set. Yeah? Because these are the D's associated with each vertex, we initialize them, and the first step says find and remove the minimum D unlabeled vertex. They're all unlabeled. The values inside the priority queue are 0 and a bunch of infinities. Okay? Does that clarify it? So 0 is less than infinity to answer the question. Okay? All right. So now we set up this for loop, and this part right here simply says, is this value less than this value? And the answer is? No. Haha. The answer is yes, it is. And so we do the update. We change this distance, this D of B, to be 2. And we mark the predecessor to be where we came from to accomplish that too. Okay, so this arrow marks the predecessor. The piece of code that does that is here. P of B equals A is how it would be instantiated. Okay, any question about that? All right, let's do the next one. Is 8 better than infinity? Why, yes. I'd rather pay $8 than infinitely many dollars. Okay, and we mark the predecessor. And again, 7 is better than infinity, and we came from here to do it. Any question? We have finished an iteration. So let's move on to the next iteration. Find and remove the minimum D. The D's label each of these vertices, right? So we still have a couple of infinities there, but now we have a 2, a 7, and an 8, and they live in a priority queue. They live in a priority queue. Which one is minimum? We're going to remove min. What does the priority queue hand us? 2, that's right. So we remove that vertex. We label it. That is, I'm going to put it behind that line. And then we do the update step. The update step involves a for loop over those 2 edges. This one gets ignored, right? Because it goes back to a vertex that's already marked labeled. And I can tell that 7 is better than infinity. Predecessor is here. Is 5 better than 8? Yes, it is. So we're going to update the 8 and change the predecessor. Okay? Any question about that? I'm going to do the first part of the next step of the algorithm. So what would be the find and remove the minimum D unlabeled vertex? We would get what? C is correct. 5 is the value, C is the vertex. So our next iteration would start like that. And end, actually. There's no updating to be done. But okay, so any questions about the algorithm itself? I completed the execution of this algorithm on this graph last time. So if you're feeling a little like, what? Go back and look at the last lecture, okay? What I want to know now, though, is what's the running time of all of this? Just as we've seen before, we have to make some decisions. We need to make a decision about our graph application or graph implementation, GRAPH, and we need to make a decision about our priority queue implementation. Okay? This is assuming we have control over all of these things. Before we launch into, let me talk about those choices. I want to spend just a second talking about the choice of priority queue. Notice it's a little bit different this time, right? Heap, yes, heap is one of our choices, but the other choice for implementing a priority queue here is an unsorted array. How can that be good? How can that be good? Well, let's look. The elephant in the room that's missing, the absent elephant in the room, is the sorted array. The sorted array. It ends up not being ever a good choice. A sorted array is never a good choice for your priority queue in this context. In a couple minutes, we'll see why. The next thing I want to ask is, which of these operations are priority queue operations? So in the top box, which of the operations are priority queue operations? This is the gimme. Yeah, step 3. This is a priority queue operation. We have to think about how to build the priority queue. For a heap, you know well at this point, it's big O of n. For an unsorted array, how much time does it take to make a priority queue out of an unsorted array, assuming you already have the array? Yeah, there it is. Here it is. Here's your unsorted array. Assuming you have the array, it's constant time. In fact, when you do this, you are simultaneously incurring the work of setting up the priority queue. Okay? When you initialize those distances, you use the D structure as the priority queue. Okay, assuming you have an iterator over it. Okay, now things get a little bit harder. I'm going to take the next one. I think this one is also a priority queue operation. Yes? Keyword was remove min, right? Priority queue is going to hand me that one. There's one more priority queue operation, and it's hiding. Can you see it? Take a look at the code. Where is it hiding? Okay, I'm going to take a journey with my pen up the screen and or down the screen. You tell me when to stop when I get to a previously undiagnosed priority queue operation, okay? Taking a trip down the screen. You're going to tell me when to stop. Whoa, that one right there? Yeah, think about what that means. It means inside the priority queue, you're changing a priority, right? This is that moment of a dynamic structure maintaining priority. So somehow, if you have access to that value, you're going to change the priority. Now, in an array, you don't care what you change it to. You can just change it in constant time. How much does that cost you? How much does it cost you to change a priority if your priority queue is implemented as a heap? Log n, that's right. Are you going to ultimately call heapify up or heapify down to do it in this example for this algorithm? Heapify up is correct because you're always decreasing the cost, right? The new one will always be less than what was before. So the new position is always going to be higher in the priority queue. Doesn't really matter that much, but it's just a kind of a touch point of, do you see what's going on? Yeah, Mark?
Is that why you can't use the sort of array because
Yes, excellent point. So he observed that this is why you can't use a sorted array, or you shouldn't use a sorted array, because the act of updating a priority in a sorted array means that you have to swap it into its new place, right? And that's expensive. That's an order n operation. So it's never the case that implementing the priority queue as a sorted array is a good idea. Okay? All right, let's see. Okay, so I think you have all of the information you need to know to do the analysis. So I'm looking at that box. If it's the case that all of the red entries are correct, which combination of priority queue and graph should be discounted outright? Which one should we just never consider? A heap and adjacency matrix. That's right. We're never going to do this because if this is the dominant term, if n squared ends up being the dominant term, we can do at least as well with one of these two options. If m log n is the dominant term, then we can do at least as well with this option. So we never need to consider the heap together with adjacency matrix. We can always do at least as well, okay? Now we're going to look at the adjacency list implementation. I'll tell you about this first term. Well, in both cases, it's true that these log n's come from heap operations, okay? So they navigate the height of a heap. This first term, n log n, is the total cost over the algorithm of this. But that doesn't surprise you because I've got n iterations. This is n iterations of, oh, I'm pointing to the wrong thing. This is n iterations of log n work. Okay, so that first term is n log n. I did it wrong. It's here. Okay, any question about that at all? Okay, now I'm going to throw it back to you for the hard part. This log n comes from this assignment. This m comes from this for loop. Please explain it to me. Why is that true? What? How much work is done at every vertex? Yeah? Yep. Oh, right, but how is it divided up between this one, this loop, and this loop? How are those M edges divided up between the grand for loop, the overall orchestrating iterator, and this one? How's it working? Yeah? Yeah, good. Good. Let me catch up with you. Yeah, you got it. Excellent. So what he said is the unlabeled vertices in the worst case for each vertex are degree of V. And rather than a constant factor of n because of that outer for loop, what we're really doing is incurring n iterations of the degree of V. So we're incurring n terms rather than a factor of n. Okay, does that make sense? And from day one, when we were talking about graphs, we knew that this total is m, or big O of m. Okay? So the total running time then is this times log n, which is m log n. Okay? All right, let's do the n squareds. Yeah, you have a question? Uh-huh. Yeah. Yeah. So certainly, even in the bottom case, it's a tie, right? It's just that if somebody already gives you this adjacency matrix, you just kind of want to, and you've got memory bounds, whatever, right? Like in some cases, if you're given an adjacency matrix, it's already implemented that way. The question becomes, which priority queue should you use? Okay? It's a good question. Okay, so now let's do the second piece here. The bottom row, unsorted array. We almost don't need to talk about it because it gets back to an algorithm that you learned in CS 125, which was finding the minimum, right, of an unsorted array. How much time does that cost you? The length of the array, that's an n. This is a big O of n operation here, and you do it n times. Now, are you worried about this update? No, because for an unsorted array, this is constant time. So the total here is big O of m, and m is bounded above by n squared anyway. Okay, so that argument applies in both cases here. All right? Now, one last question. Which is best? The answer depends on the density of the graph. For a sparse graph, what's the best implementation? Yeah, it's this one, right? Because in that case, m is big O of n. And so for a sparse graph, you use an adjacency list and a heap, and you get big O of n log n running time. For a dense graph, what should you do? Yeah, you don't really care about the graph, but you better use an unsorted array. Okay, that heap you don't need to do that much maintenance. The maintenance costs you. And so this is just, oh boy, this is a mess. Sorry. Last day and you can't read it. For dense graph, you don't care about the graph itself, and you should use an unsorted array, and your running time is big O of n squared. Okay? Any question about all that? Is it okay? Okay, we are done then with Prim's algorithm. And in fact, we're done with minimum spanning trees total. Let me see what time it is. Oh, we're good. We're good. We've got 23 more minutes to learn a whole new algorithm. You wouldn't be here if you couldn't handle it. So what I want to know from you right now is who lives right there? I need somebody that lives right there. Looks like Bartlett. Okay. All right. Now what I want to know, so raise your hand if you live really close to that red circle. Yeah, there's always somebody. All right, Neil, you live in that red circle? Okay. I want to know if when you get in your car after finals, what way do you go to get home? Okay, so hold on, let me catch up with you. So here we are right here in Siebel Center, smiling. Oh, no, we're not in Siebel, we're in ECEB. Well, that changes everything. All right, and I want to know the best way to get home. Now look what you're optimizing, right? You're going to get home as quickly as possible. That's your metric on your edges. Those edge weights effectively are the time it costs to navigate them. The graph itself is the set of possible roadways we can take to get there. Okay, so Neil, how do you go? You get to 57. I'm going to assume you go out North Lincoln, and you go like this. You go all the way to the tri-state?
Yeah, I go on to 80.
Oh, you do go on to 80. You don't have to do that anymore, you know. Because 57 now meets the tri-state. I'm just going to get this wrong.
Then I go on to 55.
Oh, you do go on to 3? Oh, man. Oh, dude. All right. Yeah, 355.
How outdated is the map?
My map may be dated. Okay, I'm saying you're going to come up here a bit. Oh, there's the tri-state. And you're going to do this? Oh, you're going to do this, you're telling me. Where the heck is 80? Oh, it's here. But now you can do this. Okay. All right. I pretty much guarantee you that anytime anybody drives from Champaign-Urbana to some suburb of Chicago, they have the conversation of what way are you going to go? And the answer is, well, what time of day are you going, right? And the ultimate objective is to minimize the total time it takes to sit in the car. Nobody really cares about the podcast that they're listening to, right? Like it really is just can I blink my eyes and get myself from here to there? That's the problem we're going to address before the end of the day. How's that possible? Okay, this is called the single source, as in here in the example, shortest path problem. And the cool thing about it, one cool thing about it, is that it incidentally gives us the cost from the source to every vertex in the graph, not just the target, not just Neil's house, okay? It'll also give us the shortest path to Kankakee. Yes! All right, and that's what we're going to talk about next. Okay, so technically the description of the problem is this. You have an input is a directed graph with non-negative edge weights. That non-negative edge weights part is particular to Dijkstra's algorithm, but non-negative weight cycles is something we're going to talk about in a second. Okay, so non-negative edge weights and some start vertex. And the output is a subgraph of G consisting of the shortest minimum total cost path from S to every other vertex in the graph. I do not know how all that happened. All right, and we're going to study Dijkstra's algorithm. Now, just to get a feel for this thing, I'm going to pretend we start at S, and I want to know, just eyeball it. What way are you going to go if you go from S to G? SCG, right, good job, okay? You're not going to bother with going this way because it takes you 7 to get to F, and there's no cheap way to get from F to G. In fact, you can't get there at all, it looks like in this graph. So we're going to go S to C to G. Now, I'm going to change the story slightly. Now, what's the shortest path from S to G? SCG, 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 SCG. Is there a shortest path? No, that shortest path doesn't exist, and the reason I know it is because if you tell me one, I can always find a shorter one, right? I can always just go around the loop one more time. This is the problem of arbitrage, right? This is why people are always looking for negative weight cycles in currency exchange, because you can get infinitely rich super fast. Well, as fast as you can make trades, right? So this non-negative edge weight is particular to Dijkstra's algorithm. Non-negative weight cycle, if there's a non-negative weight cycle, the problem cannot be solved at all, okay? So non-negative cycle implies no shortest path, okay? Any question about that? So all of the shortest path algorithms assume no negative weight cycles. The Dijkstra's algorithm assumes no negative weight edges, and we'll talk about why that's true later. Okay, so Dijkstra's algorithm, let's do it. We've got 17 minutes. No big thing. Okay, so here's how it goes. S is going to be a special vertex this time. It's the source. And our process is going to find the shortest path from S to every other vertex in the graph, assuming it's reachable, assuming they're reachable. Otherwise, those distances will stay infinity. We're going to initialize the structure. Guess how? Does that look familiar? Just like we did before. Okay? Like prims. And then we're going to repeat these steps. I bet you can guess how many times. N times. Label a new unlabeled vertex whose shortest distance has been found. I'm starting at S. There are no negative weight cycles. Have I found the shortest distance from S to itself? Yes. Okay. The shortest distance from S to itself has been found. I'm going to label it. Okay? And then I'm going to update that vertices neighbors with a better distance. Now, I know the shortest distance to S is 0. So what do I know about the shortest distance to C so far? The shortest distance we know of to C. 3, right. That is 0 plus 3 is 3. And we got to C by going this way. We're also going to update F. The shortest distance to F is 7, and we got there by going this way. Any question about that? Yeah, Jeremy? No, G is not a neighbor of S. We can only, have you ever driven the wrong way down a one-way street? Okay, I have Lincoln, Nebraska, 1983. Yeah, it's memorable. You don't want to do it. Okay, so we're only, the incident edges only originate at the current vertex, okay? All right, now the question is slightly different. So we've iterated, we've done the update step, we've iterated. Now the question is slightly different. Label a new unlabeled vertex whose shortest distance has been found. Have we found, in general, do we know that we have found the shortest distance to F? I mean, maybe for this graph, but we don't know for sure because there could be a way to get to F through C, right? But we know we have found the shortest distance to C because all the other known distances are already longer. So we're going to remove C from some priority queue, right? Label it and update its incident edges. Now, update becomes a little bit different because the only incident edge we have to look at is CG, right? But I am no longer interested in the cost of attaching G to the structure. I am interested in the cost of going from S to G. What's my current best known cost of getting from S to G? 8 is correct. It's the cost of getting to C plus 5, so it's 8 here. And we're done with that iteration. Okay, now we're going to do it again. I'm going to do the whole algorithm on this slide. Okay, we're going to remove the minimum weight cost, the minimum weight path length, because we know it's optimal. We're going to label it. So we're removing F. We're going to label it, and we're going to update its edges. So now we know that D is going to be 10. That's right. 7 plus 3 is 10, and D comes from here. E is going to be also 10, and it comes from here. And we're done. Yep. Thank you, Cortana. Okay, any question about it? Okay, let's do the next iteration. What's the minimum weight distance? What is the vertex whose minimum path has been found? We know. G, that's right. Its cost is 8. We are going to label it G, and then we're going to update its incident edges. This incident edge we're going to ignore because it goes back into the labeled set. This one becomes 7. Oh, wrong, my wrong. It becomes 15 is correct, and its predecessor is there. See why 15? Okay. Minimum weight vertex. What's the vertex of minimum weight? 10, and the name of it is D. I'm taking D because my picture will get just completely untenable if I take E. Okay, so I'm doing this. The incident edges I'm worried about are only 2. Do I update? No. Look, 10 plus 2 is 12. I can get to E in cost 12, but it's not better than the one I've already found, right? So I basically just ignore that option. Who needs it? Okay, and so we're done with D. The next one is E. Its incident edges of interest are that 2 only. Should I update B? Yes, I should, because 10 plus 2 is 12. The predecessor moves here, and we're done. We aren't quite done, right? We're going to do that last iteration. We're going to remove B as well. We're going to remove B. But all of its edges will go back into the labeled set. There are no more vertices to explore. All of its edges will get ignored, basically. Okay, where's the solution? The answer is it's all the predecessors. So B goes to E, E goes to F, D goes to F, F goes to 0, to S, C goes to S, G goes to C. Okay, so again, what we have is a spanning tree, but this time it's one that gives you minimum cost paths rather than a minimum cost total. Okay, any question about it? All right. Before we talk about running time, I want you to help me fill in this code. So this slide is pretty much copied from the Prim's algorithm slide, except I forgot the boxes apparently. But we need to change the code here in the update step. This time we have 2 terms to compare to the next D. What are they? What are those 2 terms? D of V, good. dV plus the cost of the edge weight, right, the cost of VW. Good. And then if it is smaller, then of course we're just going to substitute, we're going to update dW. And that's the only difference. That's the only difference in the algorithm. So tell me everything you need to know about the running time. It's exactly the same as this messy slide, right? If we had time in the semester, we would completely reproduce this slide, and you'd all take a nap. Okay? Any question about that? I love the fact that with slightly different input, slightly different starting point, and a teeny tiny twist to the algorithm, you can solve a completely different problem. Okay, yeah? Yep. Yep. So the question is, pointing out the distinction between undirected graphs for Prim's algorithm and directed graphs for shortest path. And what I'll remind you is that an undirected graph is a directed graph, right, with edges in both directions. So we can apply Dijkstra's to find, right. So we can apply Dijkstra's on graphs that we commonly think of as undirected, sure, because undirected is just directed in both directions. So we can apply Dijkstra's on undirected graphs. But the question is, can we apply Prim's here? Kind of. What do we expect from it, though? So the problem is that you don't necessarily have a notion of a spanning tree, much less a minimum total cost one, because the expectation of a spanning tree is that the paths are undirected paths, that there is a path between every pair of vertices on that tree, on the minimum total cost spanning tree. There is, however, an alternative algorithm that applies specifically to directed graphs that are not undirected, that relies on strongly connected components of the graph. And that actually is the subject of my talk tomorrow that I'm giving, in case you guys know, strangely. Okay, so Prim's algorithm doesn't apply to directed graphs that are not undirected because there is no notion of a spanning tree there. All right, any other questions about this? Okay, but directed graphs, or undirected graphs, they both apply to. All right, so the question, though, is why does Dijkstra's algorithm demand non-negative edge weights? What I want to do is look at what can go wrong with specifically Dijkstra's algorithm if we allow for negative edge weights, okay? So I've taken the same picture, but I'm going to start from here. So I'm going to, pretend like I update the whole thing in exactly the same way that we've done before. And we're going to start from S. All the other distances at this point are infinity. The first thing I do is label S and update its incident edges. So D is going to have cost 3, and I get there via S. E is going to have cost 2, and I get there via S, right? Okay? Now, any question about that? So that's just the normal update step. Now, Dijkstra's algorithm says that for the minimum D, we have found the shortest path. If this were a positive value, that would be true, because every other path going outside of S is going to be bigger than 2 to begin with, and we're just going to add to it. But in this example, I cannot say that we're done with E, right? Because just by eyeballing it, I know I shouldn't be done with E yet. That we can do better than a cost of 2. It's Dijkstra's algorithm that would iterate in this way. It's Dijkstra's algorithm that would look at this picture and go, oh, yay, we're done with E. Okay? When we're not, actually. So let me label that. I'm going to put it in red because this is the dangerous move. So Dijkstra's would say, okay, find and label the minimum total weight edge. That's a mistake when you allow negative edge weights, okay? Because we could go here. Now, there is another algorithm that will find shortest paths in the presence of negative edge weights, absent negative weight cycles, but it's more expensive, right? It has to keep track of more stuff and spend more time making sure there aren't alternative better paths. So it won't surprise you that that algorithm, when you see it in 374, that algorithm actually has another, I believe, factor of n in its running time. Okay? All right. That's all I have. That's all I have. You did it. You guys did it. You did it. We survived.